Hello, this video is to show how to use moment distribution method to solve a two-span continuous beam problem. Moment distribution method is a very accurate approximate method by making assumptions of the moment at each joint of the structure. By doing the assumptions, we need to use moment distribution table to distribute the unbalanced moment at a fixed connection of the structure. So today's example is a two-span continuous beam. In order to solve the problem, and first we need to cut the structure over the intermediate support. Now we break the member into two separate members, 1 and 2. Then the approximate method use approximate structure. The structure change to beam AB plus beam BC. And we notice that we use fixed support to replace the original fixed connection. So this point is our approximation. Okay, and we need to put the external load on each segment. On AB, 8 kilonewton per meter, uniform load, and the length of AB is 6 meters. And for BC, subject to a point load in the middle, the length of BC is 8 meters. (12 kilonewton to the support B is 4 meters. After that, we need to put fixed end moment. In order to calculate fixed end moment, we need to use the fixed end moment table. And first, let's take a look at the member AB. Member AB has a roller support A and fixed support B. So we will use the table fixed end moment and support conditions, one roller opened and one fixed support. So we will use this case for member AB. Okay, and for member AB, we have the fixed end moment at A equals to 0 because of the roller support. There's no moment. And for fixed end moment at B, equals to (8) WL squared. okay, equals to W times the span length squared over 8. W is the uniform load magnitude. And for fixed end moment, we have the sign convention. Clockwise is positive, so at B end is clockwise, so we use positive. Okay, and fixed end moment, now we need to calculate it, equals to 8 kilonewton times span length squared, which is 6 meters squared over 8, and equals to positive. Positive means clockwise, and positive 36 kilonewton meter. Okay. Then we move to member BC. And BC has a fixed support at B and a fixed support at C. So based on this load pattern and support condition, we notice that we need to use the fixed end moment, this loading case. Okay, the fixed end moment equals to PL over 8. And we notice that at B end is counterclockwise, so it's negative PL over 8. And on the C side is clockwise, so equals to positive PL over 8. Now we need to calculate the value based on the load pattern and span length. So now we have P equals to 12 and L equals to 8. Negative means counterclockwise and over 8. Then we get the fixed end moment equals to negative 12 kilonewton meter. And on the other side, equals to positive 12 times 8 over 8. Then equals to positive 12 kilonewton meter. After we do this approximation, we notice that there is an unbalanced moment at B. So on AB side, positive 36. On the BC side is negative 12. Then the unbalanced moment at B equals to 36 minus 12 and equals to 24 kilonewton meter. That's positive. Okay. And we need to distribute this unbalanced moment to member AB and BC until it's balanced at joint B. In order to distribute unbalanced moment, we need to calculate the relative stiffness at each joint. Now let's take a look at member AB. Member AB. First, we want to calculate the stiffness. So at A, KAB equals to 0 because it's a roller support. And KBA equals to 3 EI over L AB. So KBA equals to 3 EI over 6 meter. So equals to EI over 2. And for BC, KBC equals to 4 EI over LBC. 4 EI means both ends are fixed. It equals to 4 EI over 8. And KBC equals to EI over 2. Then to the C side, KCB equals to infinity because the original structure is a fixed support. So now we get the stiffness at each joint. Next, we will calculate distribution factor based on the relative stiffness. And first, let's calculate distribution factor at A. A is a roller support, so roller support cannot take any moment. If there is a moment, it will distribute all the moment to the other side. So distribution factor equals to 1 for roller or pinned support. And for the BA, distribution factor BA equals to KBA over the total stiffness at B. So equals to KBA plus KBC. That's the total stiffness at B. Then we get EI over 2 over EI over 2 plus EI over 2. And get distribution factor equals to 1/2. And also, distribution factor for BC equals to KBC over total stiffness at B, then equals to 1/2 as well. And for distribution factor at C equals to 0 because it's a fixed support. Fixed support will absorb any moment distributed to the joint. So it won't distribute any moment. If there's a moment transfer to C, it will absorb all the moment. Okay, so now we get distribution factor at each joint. After that, we will use the distribution table to distribute the unbalanced moment 24 kilonewton meter. Based on the relative stiffness. So now we use this table. And first, we will put the joint. There's 3 joints on this beam. So we have A, B, C. Then we put a member linked to each joint. And for A, there's only one member, which is AB. And at joint B, there are 2 members, BA and BC. And C only has one member, CB. Then we put stiffness factor according to our calculation. So AB, 0, because it's a roller support. And KBA equals to EI over 2. And KBC also equals to EI over 2 based on our calculation. And KCB equals to infinity because it's a fixed support. Then we move to the next line, distribution factor. Distribution factor also called relative stiffness. So distribution factor for roller support is 1. And distribution factor for BA equals to 1/2. And K for BC also equals to 1/2. And you can calculate the sum of distribution factor at one joint, this approximation joint. Fix the connection. The sum should be 1 because it's a relative stiffness. Then move to C, and C is the fixed support, so it's 0. Then we put fixed end moment according to our calculation. And we have the A side roller support. There's no moment, 0. And for member AB at B side, it's positive 36. Positive means clockwise. And on the BC side, it's negative 12. Negative means counterclockwise. And on the C side, it's positive 12 kilonewton meter. Means clockwise. And then we do the distribution. At B, the approximation joint, we have unbalanced moment equals to positive 36 minus 12 and get positive 24 kilonewton meter. And we need to distribute the unbalanced moment until the moment balance at B. So we use negative 24. Take the negative unbalanced moment and times the distribution factor 1/2 and get negative 12 kilonewton meter. And for the BC side, use -24 times distribution factor 1/2 and equals to -12. After that, we need to carry over 1/2 of the distribution moment to the other fixed end within the member. And member AB, also member BA, that's the same member. And A is a roller support, so it's not a fixed end. There's no carryover. And for member BC or CB, C side is a fixed support. If there's a distribution moment at B side, it will carry over 1/2 to the C side. So we'll carry over the moment at the B side within the member BC to the C end. So use -12, just this distribution moment, times 1/2. That is the carryover factor, and equals to -6. That's the carryover. After that, we'll do a sum of moment starting from the fixed end moment. So we'll sum everything from fixed end moment. Do the sum of the moment. Then we'll calculate. At A side is 0. Everything in this line. And member BA at B side equals to +36 -12, and get +24. And for member BC at B side, and we get -12 minus -12 and equals to -24. And on the C side, +12 minus 6 and equals to +6. And after that, we will take a look at the moment at B, the approximation joint. And on the AB side, the BA side, we have +24, means it's clockwise. And on the BC side, -24, means it's counterclockwise. And if we sum these two moments, and we notice, sum the moment at B equals to +24 minus 24 equals to 0. And this is our goal for moment distribution. Means that at fixed connection B, the moment already been balanced. That's our goal. Okay, so now we're done with distribution. So after that, we will take a look at those numbers. And all of those moment is our assumptions. So those moment at each joint is our assumption. And after that, the structure already reduced to statically determinate structure. And from there, and we can use equations equilibrium to solve the problem. And according to this table, now we can Draw the free body diagram for each member. And for member AB, the length is 6 meters, subject to a uniform load. (8 kilonewton meter). Then I just put the known value. We already have the moment at A. I use the green color to represent the known value. That's our assumption. At A is 0. And at B end, positive 24 means it's clockwise 24 kilonewton meter. And for the BC segment, subject to point load 12 kilonewton. According to the distribution table, we already know at B end it's negative 24, so it's counterclockwise. And on the C side, positive 6 means clockwise 6 kilonewton meter. So this is the known value based on the distribution table. So after that, we'll put the unknown force. Since we cut each member, we just put the shear force on each end. And we assume the unknown shear force is in a positive shear direction. And for internal forces, positive shear means the left end up. And right end down. That's the positive shear direction. And I would like to put this VB just left of support B. So I just put this minus sign, means left B. And for free body diagram of BC, just pass support B, left end up. VB, I put plus sign, means right of support B. And C end, right end down. Shear force is unknown. So in order to calculate the shear force, now we need to use the equilibrium of each member. And for member AB, for example, we can sum the moment at A to get VB. and then sum the force in the y direction to get VA. And for member BC, we can sum the moment at B to get VC, then sum the force in the y direction to get VB. Okay. So for member AB, we can sum the moment at A equals to 0. And get, when you sum the moment, and as long as it's consistent for positive and negative sign, it doesn't matter which direction assume is positive. When you sum the moment equals to 0. Okay? And for example, I sum the moment at A equal to 0, then I get VA past point A, and A end is 0. There's no moment contribution to A. Then I have this 8 kilonewton per meter times 6 meters and times 3 meters. That's clockwise and plus VB minus times 6 meters, and that's clockwise, and plus clockwise 24 kilonewton meter equals to 0. Solve this equation, we can get VB, just left support B equals to negative 28 kilonewton. So I just put this value on the free body diagram equals to negative 28 kilonewton. And after that, I use the force in the y direction equal to 0 to solve for VA. And get VA, if I assume positive force direction is upward, minus 8 kilonewton per meter times 6 meters, that's downward, and minus negative 28, that's the VB, minus, equals to 0, and get VA equals to positive 20 kilonewton. So we put this value on the free body diagram, positive 20. Then we move to member BC. For member BC, same thing. First, we sum the moment at B equals to 0 in order to get VC. Then I just VB past point B, no moment contribution. They have counterclockwise 24. So for example, if I sum the moment at B equals 0, I assume positive moment is counterclockwise. So it's 24 kilonewton meter. So if I assume this 24 is positive, then the 12 is negative 12 kilonewton times 4 meters because it's clockwise. Then minus 6 kilonewton meter clockwise, and minus VC times 8 meters equals to 0. And we can get VC from this equation equals to negative 3.75 kilonewton. I just put a value right here, negative 3.75 kilonewton. Then I use the force in the y direction equal to 0 for member BC and get VB plus minus 12 kilonewton downward and minus negative 3.75, that's VC, equals to 0. And we can get VB equals to positive 8.25 kilonewton. So we just put a value right here, positive 8.25 kilonewton. So that's the free body diagram. We do the free body diagram in order to draw the shear and the moment diagram for the beam. Okay, so after we get free body diagram, we can draw the shear diagram afterwards. Shear diagram is based upon the free body diagrams. So we'll draw the shear diagram next. AB, BC. Okay. There's two segments. And for AB segment, that's member 1, and we refer to the free body diagram for member 1. In order to get a shear diagram, first we need to identify the key point for shear diagram. The key point for shear diagram represents the possible maximum shear on this segment. So for the key point of shear is beam end, support, and change of external force. So we identify the key point for AB segment is just A and B. Okay, so we will draw the shear diagram for AB first. According to the free body diagram right here, and A is positive 20. B, just left support B, is negative 28. And for AB segment, only a distribute load. If there's a distribute load on this segment, means the shear diagram should be a straight line. The slope equals to the distribute load magnitude. So we connect these 2 points by a straight line. So we have positive side and negative side. Then there is a 0 shear location. In order to identify the shear equals 0 location, and this x equals to 20, divided by the uniform load magnitude, 8 kilonewton per meter, and x equals to 2.5 meter. Now let's take a look at the segment BC. Segment BC, just the path support B, is positive 8.25. On the C side, is negative 3.75. In order to identify the key point of shear force on member BC, and first we identify B is a support, C is the beam end, and as well as the point has external load change. So it's right here, the point load location. So for shear key point, we also need to identify the point under the 12 kilonewton load. Okay. Just left of 12 kilonewton load, we notice that there's no load between B and the left of 12 kilonewton, means that the shear force keep constant. To the 12 kilonewton force. And just past the 12 kilonewton and to the C side, there's no external force between these 2 points, means the shear force should be a constant between B and C, between the 12 kilonewton and C. So it's negative 3.75, just the right of 12 kilonewton, and the left of 12 kilonewton is positive 8.25. And the difference between left and right of 12 kilonewton should be 12 kilonewton. If you add 8.25 and 3.75, and if we find the difference between the 2 points is 12 kilonewton, which is equals to the point load. So we get positive side and the negative side. And this is the shear diagram. After we get shear diagram, and we can draw the moment diagram. When we draw the moment diagram, we need to refer to the free body diagram and shear diagram. AB segment, and BC segment. And first, we need to identify the key point for each segment. At the moment, the key point represents the possible maximum moment location and include the beam end, support, so we have A and B, as well as the V equals to 0 point. And at A, we already know that A moment equals to 0 right here. And B, we already know that B side is 24. And according to the direction, this 24 is top in tension, means based on internal moment sign convention, it should be negative moment at B. So when we draw the moment diagram, it's followed internal force sign convention. Means positive moment, bottom in tension. Negative moment for internal force is top in tension. Okay, so according to that sign convention, we notice that this 24 here is top in tension, so it should be negative. (24 kilonewton meter), and here refer to the internal force sign convention. So for AB segment, we already know the two key points, A and B. The only key point left is the V equal to 0 location. In order to calculate the maximum moment, we will use the moment at A plus the area between A and V equal to 0. So equals to the maximum equals to MA plus 1/2 times 20 kilonewton times 2.5 meter, and equals to 0 plus 25, and equals 25 kilonewton meter. Here. Then we can connect the point 0 to 25, and slope equals to the shear diagram. So slope start at 20 and end at 0. And then slope start from 0 and end at negative 28. And this is the moment diagram for the AB segment. And for BC, first identify those key points. BC segment. we also need to refer to the free body diagram. Key point is support beam end B and C, and also has the shear change point, which is under the 12 kilonewton load right here. No other key point. So according to the free body diagram, we already know the moment at B end is 24. Top in tension. So we already know at this point it's negative 24 kilonewton meter. On the C side, equals to 6 kilonewton meter, and also based on the direction is top in tension. So it should be negative 6. Then enter the shear change point, and we will use the moment at B plus the area of shear diagram between B and 12 kilonewton. So we can calculate the moment. Equals to MB plus 8.25 kilonewton times the distance is 4 meters. So equals to negative 24 plus 33 and equals to positive 9 kilonewton meter. And after that, we can just connect the key point. And for B to the key point, 9 kilonewton meter, shear force constant. So we connect these 2 points by a straight line. Slope constant. And after past the point load, shear force is a constant, negative 3.75. So slope is negative 3.75, straight line. Okay. So after that, we finish the moment diagram. And this is the moment diagram of the two-span continuous beam. Okay. Done with this example.